Hello, world of calculus and all who inhabit it. Today I will be looking at a super fun chart free response question for AB Calculus from 2012. This is question 3, but before we take a look at that question specifically, let's look at what the fun chart entails. So when you have a graph, say f of x, there are a few characteristics that it may have. It could be concave up, concave down, increasing, decreasing, positive, or negative. And when you have f prime, the derivative of f of x, you can look at these characteristics and you know something about f prime from f. So when f is concave up, you know that f prime of x is going to be increasing. You know when it's concave down, it's going to be decreasing. When f is increasing, f prime will be positive. When f is decreasing, f prime will be negative. And you can't really tell anything about f prime from whether f is positive or negative. And then you can go a step further and look at the second derivative of f of x, f double prime. And again, if f of x is concave up, f of prime is increasing, and when a function is increasing, its derivative is positive. So derivative of f prime is going to be positive when f prime is increasing, and then when f is concave down, first derivative decreasing, second derivative negative. And again, you can't really tell anything from the positive or negative. And then there is a fourth element to the super fun chart. You have g of x, and g of x is defined as the integral of f of x. And since g of x is the integral of f of x, you can also think of it as the antiderivative to f of x. So you kind of think backwards here. So when f of x is increasing, you know that its antiderivative is going to be concave up. When it's decreasing, you know that its antiderivative is going to be concave down. When it is positive, you know that its antiderivative is going to be increasing, and negative will be decreasing. So now let's take a look at our specific problem. We have 2012 question 3. You are given the graph of f, so your home base here, the graph of f of x, and it says, let f be the continuous function defined on -4 to 3, whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. Let g be the function given by g of x equals the integral from 1 to x of f of t dt. Alright, I have the graph drawn for you here. So the first part of the question asks us to find g of 2 and g of -2. So we know that g is the antiderivative or the integral of f of x, which we are given in our graph. And g of x is defined as the integral from 1 to x. So when we find g of 2, we are going to be integrating from 1 to x. So in order to do that, integral equals area. So we're going to be finding the area from 1 to 2, which is a triangle. And in order to do that, we look at what the slope of this line is, and we see that it is -1. So since this point is at 1, 0, we know that this point is going to be at 2, -1/2. And you can have a negative area when your area is below the x-axis. So what we're going to do is we're just going to use the formula for the area of a triangle, which is 1/2 base times height. Your base is integrating from 1 to x, so 1 to 2, which is a difference of 1. So base of 1 times your height, which we found this point to be 2, -1/2. So your height is -1/2. And you work that out, and that ends up giving you -1/4 equals g of 2. Okay, so now it asks you to find g of -2. And since, again, we're integrating from 1 to x, we're going to end up integrating from 1 to -2. And since we're going left along the x-axis, we're actually going to be integrating backwards. So we're going to end up finding our area and basically making it negative. Okay, so let's start with -2, and we look at this segment that we can work with right here. That's a triangle. So we start off with, again, the formula for the area of a triangle. So it has a base of 1 and a height of 1, 2, 3. Wow, that's an awful eraser. And then we look at this portion, which it tells you is a semicircle in the problem, right there. And we look at the area of a circle, which is pi times the radius squared. And since you're given this point, 1, 0, you can see that the radius is just 1, and 1 squared is 1. So if you had a full circle here, your area would just be pi, but since we have a semicircle, it's going to be pi over 2. And since the semicircle is below the x-axis, it is going to be negative. And since your limits of integration are from 1 to -2, you stop there since this is at 1. And you work this out. That gives you 3/2 minus pi over 2. But since we are actually integrating backwards, since you're given the integral from 1 to x, we're working 1 to -2. Again, you end up making this whole thing negative. Yeah, so that's going to end up giving you pi over 2 minus 3/2. So part B asks you to find g prime of -3 and g double prime of -3, or state that it doesn't exist. So we know that when you're given g, that means it's the antiderivative of the function that you're given. And it asks us to find g prime of -3 and g double prime of -3. So when you're finding the derivative of the integral, you're finding the derivative of an antiderivative, which is the same thing as what you're given with. So when you're finding g prime, you just look at f, because your derivative and your antiderivative just cancel out. So you look at where -3 is on your graph, and that's going to be halfway between the points that you're given here. So you find your slope here, which is just 1, and then look at where -3 would be, and you see that it would be 2, and your answer for g prime of -3 is indeed 2. Okay, now define g double prime. So look at g, and then prime is its derivative, so go down 1, and then double prime, go down another 1, and that's going to be the derivative of f of x, which is the graph that you're given. So the derivative of anything is its slope. So what we're going to do to find the derivative of f is at -3 is just find its slope at -3. So what you're going to do is use your slope formula, and you do rise 3 minus 1 over run -2 minus -4, which ends up giving you 3 minus 1 over -2 plus 4, which gives you a value of 2 over 2, which equals 1. And there is part B. Okay, so the next part asks us, find the x-coordinate of each point at which the graph of g has a horizontal tangent line. For each of these points, determine whether g has a relative minimum, relative maximum, or neither. And to justify our answers, which is also important. So we're looking for... Okay, so a horizontal tangent line would look just like a horizontal line, which means that its derivative, its slope, would equal 0. So we just need to find where g has a horizontal tangent line is where its derivative is 0. And we look at g, and we see that one step down, the derivative of g is f of x, which we're given in our graph. This is the graph of f of x. So all we need to do is find where it crosses 0, which happens at -1 and 1. And our reasoning on fun chart problems is also really important when they ask. And the reason is because g prime of x equals f of x, and f of x crosses 0 at those points. Now we need to find whether these points represent a relative minimum or a relative maximum on the graph of g. So when a graph has a relative extreme, that means it's either changing from increasing to decreasing at that point, or from decreasing to increasing. And when that happens, that's where it hits a pretty low or pretty high point on that graph. So what we need to do to see whether these points are relative minimum or relative maximum or not is look at the derivative and see whether it changes from positive to negative, which would mean our antiderivative, our original function, changed from increasing to decreasing, which would be a relative maximum, or vice versa, which would be a relative minimum. Or if it did not go across the x-axis, it would be neither of those. So we look at our graph, and we see that at -1, at -1, f of x, which is the derivative of g of x, changes from positive to negative. And when that happens, that means that the graph of g went from increasing to decreasing, which means that it had a relative maximum there. So x equals -1 is a relative max because g prime of x, which is equal to f of x, changes from negative to positive there. And now we look at x equals 1, and we see that the derivative of g, which is f of x, does not actually go across the x-axis, which is a key point here. If it does not cross the x-axis at all, if its derivative doesn't cross the x-axis, then it does not have a horizontal tangent line there because it didn't go from increasing to decreasing. So at x equals 1, neither a rel max or min, because again g prime of x, which is equal to f of x, did not change signs there. Okay, the last part. So D asks us, for the interval, find the values of x for which the graph of g has a point of inflection. So a point of inflection is where a graph changes from concave up to concave down, or vice versa. So we're going to look at what that entails for the graph of f of x, since that's what we're given. So when g changes its concavity, we know that f of x is going to change from increasing to decreasing, or vice versa. So we look at our graph, and we see that it changes from increasing to decreasing at -2, changes from decreasing to increasing at 0, and it changes from increasing back to decreasing at 1. So you're going to say that g has a point of inflection at -2, 0, and 1 because g prime of x, which is equal to f of x, changes from increasing to decreasing at those points. And